friends. Now we are discussing about the continuation of frequency response unit 2. So in that unit 2 we have the one more topic, that is nothing but parallel resonance. Right now, so this parallel resonance is also called as the anti-resonance. The parallel resonance is also called as a anti-resonance. Now consider the RLC parallel circuit. The circuit of RLC, which is like this. So now this is the circuit or else parallel or LC circuit. Now here R and L means inductor and resistance, both are connected in series, right? And this is called as a coil, or in the combinations of the series combination of the resistance and inductors, this is called as a coil. The combination of R and L, the series combination of the R and L, which is connected across the XC, that means capacitor. Okay, so now whatever it may be the circuit, so the circuit, the capacitor which is connected across the parallel to the combination of series combination of the R and L only, right? Consider the parallel RLC circuit. Since this is a parallel circuit, admittance, and now we can, for our convenience, we have to consider the admittance of this circuit. That means what is the admittance? Y. Y is nothing but what? G plus J into B, right? Now here, so what is G? G is nothing but what? Conductance. That means reciprocal of the resistance. B is nothing but what? Susceptance. It is the reciprocal of the reactances. Reactances of what? Reactances of inductor or capacitor, right? Now see, here the combination of impedances of the coil, that is nothing but what? Admittance of the coil, YL. YL is the, and the series combination of the RL and XL, right? Now, so 1 by R plus J into XL. So what is the impedance? Z is equal to R plus J into XL for the series RL circuit. Now admittance is nothing but a reciprocal of the impedance, so that YL is equal to 1 by ZL means what? R plus J into XL. Then we can, YL is equal to RL minus J into omega L by RL square plus omega L whole square, right? And what is YC? That is the admittance of the capacitor. That means 1 by impedance of this capacitor means XC. XC is equal to 1 by J into omega C, but it is a reciprocal of the impedance, means it becomes 1 by J omega C. Then YC is equal to J into omega C. Now the total admittance, which is equal to YL plus YC, then it becomes what? YT. That means total admittance, which is equal to, now we can substitute YL plus YC, then it becomes like this. At resonance, already we know that the susceptance part is equal to 0, but whereas in the case of series circuit, the reactance part will come to 0, but in the case of parallel resonance condition, parallel resonance circuit, the susceptance part is equal to 0, right? Now we can find the resonant frequency for the parallel resonance circuit, and that it becomes omega A into R, omega A R C, which is equal to omega A R L by RL square plus omega A R square plus L square, which is equal to what? RL square plus omega A R square L square, which is equal to L by C. That is the equation number 1. Then from this one, omega A R is equal to square root of 1 by LC minus RL square by L square. And from this one, omega A R is nothing but what? 2 pi F into A R. Then F into A R is equal to 1 by 2 pi root of 1 by LC minus RL by L whole square. So this is the resonant frequency for the parallel resonant circuit, Now we can find the impedance of the circuit can be obtained by considering the real part of the total admittance, right? Now we can consider the real part of the admittance circuit. The YT is equal to RL by RL square plus omega square L square plus J into omega C minus omega L by RL square plus omega square L square. Then the real part becomes to 0. Then the impedance ZAR is equal to 1 by real part of the total admittance, then which is equal to 1 by RL square plus omega AR square into L square. Now this becomes ZAR is equal to impedance of the parallel circuit, which is equal to RL square plus omega AR square L square by RL. Then from this one, ZAR is equal to L by C by RL square, right? So from equation 1, right, we got from this one equation 1. So ZAR is equal to L by C into RL. Now, so already we know that in RLC parallel circuit I naught is equal to V by impedance, then I naught equal to 1 by ZA. That means here the impedance which is inversely proportional to the current value, right? So variation of susceptance with respect to the frequency, how the susceptance values are varied with respect to the frequency. The graph which is represented the variation or changes in the individual susceptance, that means inductive susceptance and capacitive susceptance with respect to the frequency is called as a susceptance curve, right? And now we can consider the capacitive susceptance, that is represented by the B suffix C, and it is a straight line. Why? Because both are proportional to each other, right? So that is the representation of the BC versus frequency. Now here the BL is nothing but what? Susceptance of the inductance, inductive susceptance, which is inversely proportional to the frequency. Now here it is called as a hyperbolic curve. If we consider the total susceptance, that is the net susceptance, that is BC minus BL, the frequency at which the total susceptance curve crosses the frequency axis is the at the resonant frequency, right? We can consider the net susceptance of the parallel or LC circuit, then which is crossing the frequency axis at resonant frequency omega naught. Now we can see the different parameters, variation in the different parameters with respect to the frequency. So as you are seeing in the case of impedances, admittances, current variation with respect to the frequency in the case of series resonant also. Similarly, and we can see the variation in the impedance, admittance and current with respect to the frequency in the case of parallel or LC circuit also. Now we can consider the total impedances of the RLC parallel circuit is given by Y is equal to G plus J into BC minus J into PL, and Y is equal to GL plus J into BC minus BL, right? At resonance Y is equal to G. Why? Because the net susceptance which is equal to 0, right? Whenever the resonance condition may occurring, then the susceptance part equal to 0, then obviously here the admittance which is equal to conductance G only, right? So which is it is greater than the G at all the frequencies except the resonant frequency, then Y is minimum at resonant frequency, that is nothing but omega A into R. Now we can see this one. This is the curve of the admittance with respect to the frequency, right? So now at this resonant frequency it is minimum, the value of the admittance is minimum, but all other frequencies it was a maximum. So it is inversely proportional to the admittance of, that is called as the impedance, so that obviously we got the inverse of the admittance curve.